Okay, perfect. So so hash tables. Hash tables. Also, sometimes people refer to them. Sometimes, at least in programming, some people could refer to them as dictionaries, even though they might be a little bit different. Some people might actually say they are different, but I mean they are both almost the same. And the hash tables are, in general, has been introduced to answer the question of how to search for data in less than a linear time or logarithmic time. Okay. So let me actually write this down as well. So hash tables has been introduced to answer the question. Oh, let me add a little bit more space there. Uh, um, of how to search for data in less than linear time or logarithmic times. Okay. So imagine, let's talk about let's evolve the whole thing. So let's talk about, for example, linear search. Okay, so linear search. What a linear search will allow you to do is imagine that if I give you numbers like 1, 2, 4, 0, 8, 7, and 6, for example, and I ask you to find an element. Okay. Let's say I would like to find number 6, for example, and this is unsorted array. What will happen is you're going to be actually looping on every element, trying to find your target, right? And this is actually taking a little bit longer time, right? So if you have a million elements, you have to like go over, like in a worst case scenario, if your element is at, say, at the last index, for example, you're gonna be like looping for a million times until you get, or a million minus one, whatever, until you get to the until you get to your target. So basically speaking, a linear search having a complexity of O of n, right? Order of n, and this will allow you. This is happening um, because we are checking for each element until we find the target, right? So until we find the target. Okay. Sorry. All right. So this is bad. This is not good enough. So what people would say? Okay, fine. Let's actually do binary search through the array, right? So we say binary search. So in binary search, uh, which is gonna be covered later, by the way, we're gonna talk about it later. has a time complexity of O of log n, right? So, and it is O of log n because we are dividing our problem in half each step. What does that even mean? Right? So in a binary tree, so if you actually organize your data, let's say in a binary, in a complete binary tree, so it's going to be something like this, right? And this is right now a complete full binary tree. So what you will do, we will actually like search, you say, okay, and if and actually can even think of it like, okay, let's we'll talk about the maximum heap, for example, we are searching through the maximum heap, for instance, where every node is larger than the two children, for example, or something like that. So you can say, okay, I'm actually trying to search, for example, for this number, and then, for example, you say, okay, is this number is larger or smaller? So if it is larger, you go, for example, to the right, let's say. And then you ask, are you larger or smaller? So say smaller. So you go to the left, for example. So you are actually like halving the problem. So you were considering the whole tree. Then once you actually like picked up a path, half of the tree has been ignored. And then when you picked up another path, like the other half has been ignored. So you narrow it down to this target, for example, right? So practically speaking, you are like halving your problem each time. So you don't need to check for every and each element, but what you do is like you check for like you are halving your problem every time. And this is a log n. The problem here is, however, we would like to break that barrier. This is also still slow, right? And not only that, but it has a prerequisite. So we need to have we need to have already organized, already sorted / organized binary tree, for example, right? So there is this overhead that you need to prepare your data to take that form first, and then you can actually start performing the search, right? You cannot actually have just a simple array and then you can actually like, let me search through it. But no, you need to prepare, you need to make the binary tree first, according to whatever rule is going to be, which is going to be sorted at the end or organized in a certain, by a certain rule at the end. And then you're going to actually perform your task, right, with all the searching itself. So how can we break this barrier? If we would like to break this barrier, we enter the hash tables. So we go with hash tables. And hash tables has an average, oh, average search time of O of 1. However, it depends on the implementation. So, however, depending on the implementation, it might consume more memory. Okay. Sorry. All right. So we're going to talk about it as an abstract data type. Okay. So what are the possible operations that a hash table supports? Okay. First of all, in a hash table, so in hash tables, we insert elements into the array while calculating their index. These elements are located in something which we call the key space. Okay. So let me actually write this down. So when we insert elements into the array, ooh, I'll put this into the array. We calculate their index, or yeah, its index, because we are talking about a single element here, right? Or elements. Oh, then it's actually a plural, so their index. Okay, these elements are called, or they actually located. These elements are located in a hypothetical, like we call this it's a hypothetical thing. We are located at the key space. There is nothing, it just, we call it that way. It is nothing specific about it, like in the PC, just we call with the math and everything in there, we just simply call this is what we call like a mathematical model, nothing physical, if you will. Okay, so it's a mathematical model. In terms of mathematical perspective, it's called the key space, and that's it. Okay, so what are the operations? Operations. So one, you actually insert an item. You delete an item. And when you search by a key. Oh, hang on. Probably I need to change the battery on the pens, maybe. That's why it's a little bit janky these days. All right, so this is basically the operations. Now, we said it's actually a hash table. So there are hashing techniques actually. Like how can we actually like insert an element and retrieve it in O of 1 on average, right? So let's talk about the hashing techniques themselves. So hashing, let me just draw a line here. So hashing techniques. Okay. So a simple hashing technique would be achieved by calculating the value of the key or element, and use that value as an index to the array. Okay. So for example, let's say that you have an element like 9 or 14, 7, 5, and 10, let's say. Okay, let's say you have these elements. what you would do is that you say, aha, okay, fine, I'm just going to take this and I'm going to insert it into the array. How I'm going to calculate the hash? Well, the hashing function is going to be h of x equals to x, okay? Meaning that if I take this and translate it into code, it will be something like it's going to be, let's say, int h, right? It takes another int int x, and right here we just simply say return x. This is what this is saying, okay? This is the indexing, like this is my hashing. This is obviously useless in this time being, but we're gonna see different hashing techniques. But this is like a simple one. It's just simply say, give me, like I give it x, it just returns it to me back. There's nothing fancy about it, right? Okay. So what you're gonna have is, for example, like based on this hashing technique, you're gonna have, for example, an array of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And yeah, I think it is enough, or maybe, okay, let it be 14. There we go. Okay. And right now you say, okay, according to this hashing function, what I'm gonna do is I'm gonna just simply say, okay, insert 9. So look at 9, give me the index which I'm gonna insert it at. So I'm gonna use my hashing function, which says x equals to h of x equals to x. So basically speaking, 9, store it at the index 9. So it's gonna be right here. 4 is gonna be at index 4. So it's gonna store it to me right here. 14, it's gonna be right there. 7 is going to be right here, similar to counting sort, right? 5 is going to be right here, and 10 is going to be right there, right? So this is basically your storing, right? You already stored the stuff in your quote unquote your hash table. The problem with this technique is that it consumes problem with this problem that it will consume huge amount of memory. Okay, which is obvious, right? You are just simply like indexing basically through the array with this hashing function, right? So you're gonna say, aha, all right, let me actually make this a little bit better, right? You could say, okay, I would like to make this a little bit more optimized. I will not use this hashing technique, even though right now I'm getting O of 1 access. Right now it's literally O of 1. So the operations here, if I say I would like to retrieve number, I would like to retrieve number 9. I just give it the key, which is, for example, the 9 right now. It will just return to me 9. So I will get it like I say, aha, okay, at 9, give me this number. So it will give it to me, right? So this is how I can retrieve the elements, just simply search by the key. Now, how can we make this better? So you could say, okay, instead of having such a hashing function, I will just modify it a little bit. So let's say we modify, let's modify the hashing function. I don't want to consume that much memory. I would like to be a little bit more practical. Okay. So what you would do, you would say, okay, my hashing function is going to be h of x is going to be equal to x modulo the size of the array. Size of array. Okay. For example, let's say we're going to have an array of 10. Okay. So if the size, so if array size equals to 10, okay, 10 elements in there, then we have h of x equals to x modulo 10, okay? So let's see what this will give us, right? So imagine that we have an array that has, for example, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so right now I have an array of size 10. And I would like to insert, for example, 9. So if I would like to insert 9, I would say, okay, h of 9 equals to 9 modulo 10, which is going to give me 9, right? So I say, okay, at index 9, put me 9. Okay, so the guy also says, okay, let's actually insert 4. So 4 modulo 10 is going to actually give me 4. So I'm going to insert 4 right here. Then comes along and says, okay, let's insert 14 modulo 10 is going to also be 4, right? And right now we run into a problem because 4 is already occupied, right? And I cannot insert 14 here. So right there, because of this, we get a collision. Oh. And this is how it's actually called, a collision, literally. Okay. So how can we resolve this? So even if you are actually if you change the hashing function, by the way, so you say, okay, I want to actually like have x modulo 10, I'm going to have x modulo 10 plus 1, for example, whatever. You're going to still have collisions. So whenever you are trying actually to change it, the possibility of collision will still exist. But we need to resolve this gracefully. Like if a collision happens, your system or your data structure, like while you are programming, it should actually not give you an exception or shouldn't break. It should actually work immediately right out of the box, like without any issues whatsoever. So what are the collision resolution types? That's the question, right? So collision resolution types. Under open addressing, this is a category, by the way. You have something which is called chaining. You have something which is called linear probing. You have something which is called quadratic probing. You have something which is called double hashing. Okay. We have something which is called perfect hashing. Then we have something which is called universal hashing. And I think this is pretty much it. Yeah, this is like pretty much the most famous ones that like you might actually see. For those who are interested, by the way, in C#, you have something which is called a hash table. But this is the non-generic version. The generic version is called the dictionary, by the way. So you can actually see a dictionary is an array of key value pairs. And you search a dictionary by a key, you index into it by a key, and then it will give you a value. It's actually quite well known. So I think it was called T key and T value, I think, or something like that. Hang on, I think it was called like this, though, dictionary. Of T key and T value, I think. This is how the signature looked like, at least. Hash tables is the non-generic version. But nobody uses this, I think. Oh, I mean, unless you are doing something else, I don't know what. But usually people are using the generic version. I think Java has it called the hash tables. I don't know if they have something which is called dictionary there, but I remember seeing hash table like as a word in like a data structure, like in Java programming language. I think it was called hash tables for sure. So yeah. So if you would like to use hash tables as a concept or as a data structure, you have it already in C#. It's just called dictionary. Okay. I mean, at least the generic version of it. Okay. Now let's actually see. Let's see each one of these types. Okay, really quick. And believe it or not, it's like once you get until, let's say, this point, let's say, it's actually like it's a breeze from there because all of them are actually similar with minor tweaks. There's nothing fancy or difficult about this. So let's talk about chaining. Chaining. Okay. Trying to make an H here, but CH. Okay. So how chaining would work? Chaining, basically speaking, is that you are trying to make array of linked lists, practically speaking. So assuming, oh, hang on. Assuming that my hashing function is going to be h of x is going to equal to x modulo the size of the array. So let's say so. And you have a key space. In your key space, this is what you are trying to insert. So 8, 3, 13, 6, 4, and 10. And then you have an array of, so you have an array like a, hang on. So index of 0, 1, oh, hang on, let me spread them out a bit. 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so assuming that you have an array that big. Okay, and what happens is you're trying to insert into the array. So for example, you can say, okay, I would like to insert 8 right now here. So what will happen is that you are not going to actually insert it right in the array. Like, you will not say 8 here. What you will do, you will simply say, okay, I'm going to have a linked list right here, and I'm going to have 8, and then this actually points to null, right? So it's a linked list, so it's just there's nothing after 8, so it's null. Let's say I would like to insert 3, so 3 is going to be right here, and then it points to null, right? And then when it comes to say insert 13, it's okay, I'm just going to put here 13, and then points to null. And then would like to insert 6, so 6, and then also points to null as a linked list. And then 4, you're going to put 4 points to null. And then 10 is going to be 0 because 10 modulo 10 is going to be 0. So it's going to be here 10 pointing to null. And that's it, right? Hopefully I didn't forget anybody. Now, obviously, this is not super efficient if you think about it, right? So when retrieving the elements, what you will do is say, okay, I would like to retrieve element 13. You will actually put this into a hashing function. So you say 13, you would like to retrieve it back, you insert it here, it will say to you, okay, it's going to be 3. You go in there and you say, okay, are you 13? No. Then you move on to the next one. Are you 13? Yes. Then it will actually fetch it out. There is a possibility if you have a very, very bad hashing function, one of these linked lists are going to be actually quite long. And all of a sudden, you are actually not having, you are actually like getting closer to O of n. You are simply just getting closer to it, right? You're going to search through a lot of elements in the array just to get to that, or a lot of elements in the linked list just to get to that number which you need. However, this is one of the methodologies how to just simply like resolve the actual collision problem, like, right? Because whatever mathematical thing you're pulling off, there will be always collisions. You're just simply trying to minimize it. So they say, okay, fine. Let's actually try something else. The other thing which we could try is something which is called linear probing. Yep. And a linear probing, if I assume that you have a hashing function h of x, which is equals to the x modulo the size again, okay? And you have a key space that you would like to insert stuff, so 4, 9, 4, 14, 7, 5, and 10, okay? And you are trying to insert stuff. So if we have an array that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, and that's it. And you're trying to insert these elements using this hashing function. So you say, okay, 9 modulo 10 is going to be 9, so you insert 9 right there. 4 modulo 10 is going to be 4, so you insert it right here. 14 modulo 10 is going to be 4, so we have a collision. Because when you get here, you will see this part is occupied. So what you would do, you say, okay, I'm going to scan the next empty. So you're going to scan the next empty, then you find out that the 5 is actually empty, so you put here 14. Okay? And then you say 7, so you're going to actually insert here as 7. 5 modulo 10 is going to be 5. 5 is already occupied. You scan for the next empty element, and then you say, okay, 6 is empty, so you're going to put 5. 10 modulo 10 is going to be 0, which is going to be right here, right? And you have finished inserting. Now, the idea here is what will happen is that when you try to retrieve, for example, number 5, let's say, you will go here, and you will discover that 5 doesn't exist, because this is not your element which you are searching for. So you say, okay, let me look ahead. Let me increment the counter, right? So you increment the I, let's say. So you go forward, try to find the next element which you are searching for. And then you say, okay, at index 6 right now we have 5, take 5 and retrieve it. Now, this is also not super efficient, to be honest. And in fact, like when you think about this, linear probing, in fact, is having a different kind of hashing function right now, rather than just simply this. Because what happens is when you have a collision, you start to increment your index to go forward. So practically speaking, the actual formula for this is not only that, but in fact, we can modify it a little bit. we can say that in case of collision, so we're going to have another hashing function, which is going to be h of x plus f of I modulo the size. Okay, where f of I, it will simply give you, like, increment these numbers for you, right? So it's going to be just simply return to you I++, practically speaking. So if you are programming this, you have int f, oh, sorry, you have int gigantic little f, which takes an int I, and you have here return I++. Okay, so that's basically what you are doing. You just simply increment the I. So if you try to plug in the stuff here, look at this. So if I say your I will be always 0 because you are beginning it with 0 because there are no collisions yet. So what you say, okay, I would like to find number 5, for example. So you insert 5. So h of x is going to be actually x modulo the size, which is 5, plus 0. Modulo the size is 5. So you're actually here, right? You figure out it's actually 14. What you will do, you will actually just simply plug in the next iteration. So the next iteration is going to equal to this, h of x plus f, it'll be like this. So you plugged in the 5, I don't know, and this was 0 at the beginning. Right now, you're going to have here 5, and then you're going to have here I plus 1, right? This is what's going to happen. Like, you increment this I, modulo the size. Okay, so right here is going to be 6, isn't it? So 5 modulo 10 is 5 plus 1 is going to equal to 6 modulo the size, which is going to be here. So you actually get this number right here. So you say, are you the number 5 which I'm seeking for? Yes, then it retrieves it. Okay. So basically speaking, this is what linear probing looks like. This is how would you program it, for example. Does this make any sense? People?
It does.
Okay. Okay. It actually, right now, this is like, I would say this is the most complicated bit of it, because the rest is simply iterating over the same idea. So for example, this is called the linear probing, right? So quadratic probing. Quadratic probing, similar to linear probing. Okay. However, it actually tries to avoid the clustering of elements. It tries to avoid clustering of elements. Because if you have noticed, right now, when we actually start to fail because of collisions, we start to scan for the next empty spot. All of a sudden, we started to get like stuff condensed into one place while the rest of the memory is not almost used, right? So we are trying to reduce that by using something which is called a quadratic probing. So it's actually identical to it. The only thing is just it's going to have a slightly different hashing function. So, however, well, actually, it has okay, so avoid clustering and oh, and it has slightly slightly different hashing function. Okay, so if you have h of x equals to x modulo the size as the base for calculating the actual index, right? This is your hashing function. When you are trying to resolve the collision, so h dash of x is going to equal to exactly the same thing. So h of x plus f of I. However, modulo the size, obviously. However, f of I is just going to give you I squared. It's just going to square the I for you. So practically speaking here, it was f of I gives you I back, right? So if you give it 0, it will return to you 0. If you give it 1, it will return to you 1. So plug in 1 here, it will give you 1. Plug in 2 here, it will return to you 2, right? It is here, if you plug in 0, it will return to you 0. If you plug in 1, it will return to you 1. However, if you plug in 2, it will return to you 4 because of I squared, okay? And this is what quadratic probing is all about. Nothing else is, there's nothing else there, right? It's just a different hashing function with a different like I, and they call it quadratic probing. It's statistically have shown that you have a little bit more spread out um, elements in the array. So it's a little bit more evenly distributed, a little bit. Now, there's also a very interesting concept here beside this, or like beside the idea of quadratic probing here. What happens if you don't find the space anymore? That means that your hash table is actually full. Okay, so what happens if I actually search for an element and I cannot find it? That means that this element doesn't exist, right? So if I actually like find the index, indeed, yes, I found the index. So let's say I'm trying to find a number called like number 15. So 15 modulo 10 is going to give me here, right? So it will return to me here. However, this is 14, not 15. So you will actually keep moving until you try to find 15. So it's not here, not here. This is empty. That means that 15 doesn't exist, right? So there's this also part of the scanning bit. If the element doesn't exist, it will actually start scanning until it finds it. All right. This is also, I just wanted to mention, just out of completeness here. Do you have any questions so far, by the way?
No question.
All right. If there are no questions, let's move on with double hashing. Actually, I'm gonna finish this really quick, so there's no need for break because I mean it's actually relatively easy, and we have like a couple more hashing techniques to mention. This is it. So double hashing, and it's man, the pen is so glitchy. Double hashing. All right. From the name, I guess you already have figured it out, right? You just simply hash the thing twice. This is pretty much it. Okay. So similar. Oh, okay. Sorry for that. It's just, yeah, the even like actually like my handwriting doesn't look exactly like this, but just that the whole thing is like when I record the screen, apparently like Microsoft has something wrong with when you record the screen with Microsoft Teams and writing with pen. It just drives the pen a little bit crazy apparently. Like the lines do not even align even when I'm writing. To linear and quadratic. Double hashing. Relies on two hashing functions. Relies on two hashing functions. Except we use them just in one formula, right? So the first hashing function would be, so if you use the first hashing function, it's going to be h of x. So this is the first one, right? So let me write it in a little bit better way. So 1 h of x is going to equal to x modulo the size, right? And then you hash it again. So this is h1. You hash it again, h of x equals to m minus x modulo m. Okay? Where m is in fact the relatively closest prime number to the size. To the size of the array. And I got this from the art of programming. So source, the art of computer programming. I think I already have mentioned to you in the beginning of the semester. It's like an amazing resource for all developers out there, whether you're a software engineer or a computer scientist or whatever. So practically speaking, what will be your final hashing function? Like how this would look like? How can I would like to put this all in one function and just plug it in, right? So your final hashing function would look like this. So if you're trying to hash so I'm going to put this as a capital H, right? Your final hashing function is going to be h1 of x plus j h2 of x. Okay? So you already know the first one, so h1 of x and h2 of x, but what is j, right? So j is any numbers from 1, 2, 3, 4, and so on and so forth, right? This is what j is. And you increment j, so increment j on collisions. Okay? So if you find any collisions, you increment just j, and that's it. Because 1 times whatever here is going to be the same thing. That's why j is irrelevant here. But however, if you find a collision, you just increment j to 1, and it's going to be 2, right? So whatever that h2 gives you times 2, right? So that's the That's the idea here. That's it. Now, you need to have like, so this is basically speaking double hashing. Now, we go into two more. One of them is called perfect hashing. Okay, and perfect hashing is like, maybe it might actually perform bad in insertion or deletion. However, it actually have a very good however, it's very good to have a very good seeking time. So you have actually like two hashing it's not going to be like so perfect hashing is practically speaking a hash table of hash tables. Just to be clear here. So it is good for searching in a hash table. Okay, or what we call, i.e., static hash set. Right, something that doesn't change. Hash set that it just doesn't change, just you get it as it is. Performs relatively bad. Wow, the pen is really going nuts. Performs relatively bad. When it comes to insertion or deletion. Or deletion. Okay. So it has a similar idea or has a similar idea as a similar idea to chaining. Chaining, except it uses hash tables instead of linked lists. Okay. So if you have a hash table, right? So if you, let's say you are indexing here, you're gonna index, for example, you're gonna index here with h of x equals to x modulo the size, for example. Then let's say you have a collision. You're gonna actually like have another array, so you're gonna have like hash tables, right? It's just another hash tables. And when you index here, you index with a different hashing function. So if this is h1, you're gonna have, for example, h2. You're gonna have something like h2 of x is, let's say, is gonna equal to, I don't know, we can actually steal from here. So you can actually have, say, m minus x modulo m, for example, right? So when you are hashing, all right, you can actually like find the index, find the array, and just you simply insert there and you're done. When a collision happens, you can actually use a different hashing function to insert into this second hash table. So because it's practically speaking hash tables of hash tables. It actually makes finding things faster. Maybe it might perform a little bit worse when you're inserting things, but finding things becomes relatively faster. You are approaching the O of 1. as much as you can. Let me actually give you the final one. So this is like perfect hashing, universal hashing. And universal hashing is actually quite interesting. So it relies on having a collection of hashing functions. Of hashing functions that we can pick at random and we stick with it through the runtime out, so throughout the runtime of the application. So let me write it down so that we, whoop. Okay. Let we pick at random. And we stick with it throughout the runtime of the application. Okay. So so what would be actually what this would look like? Like, for example, let's say you start the application and it will use just a hashing function, all of the hashing functions. And you start actually like, keep using it, and then when you run the application again, it just picks up another hashing function. Some people actually might use a collection of hashing functions. Let's say, like, for example, in let's say here in double hashing, for example, you could have two hashing functions in the runtime, and then when you run it again, you will get like two different another two hashing functions. So statistically speaking, every time you run the application, you might have, for example, lesser collisions, and you might have better memory access in some cases, statistically speaking. So how can you calculate this thing? How can you actually make this one? I think also I got this from the Art of Computer Programming. So you choose a large prime number. There's also like a suggestion for using like kind of universal hashing generator functions. So so we start by choose a large prime number. We call it P. We have B, which belongs to, this is not E, this is like, I'm trying to force the pen to follow me here. We have B, which belongs to numbers from 0, 1, 2, until P minus 1, which is that P, right? And then we have A, which belongs to the collection or the set of numbers 1, 2, 3, and P minus 1. Okay? Your hashing function of A and B, so you give A and B, different A and B every time. and you're trying to hash a key, or the X, doesn't matter. It's going to be A times K plus B mod P then mod M, or where M is the closest prime number to the size of the array. Okay, the same M from here. Okay, where is M here? Where did I define M? Yeah, this is the same M. Okay, and this is universal hashing. This is what it's all about. Hash tables as a data structure. I will actually stop recording here.